The next class that we have is a driver. Now here, the driver and the monitor are the most crucial classes because there you need to do a lot of work depending on the specific sequence that you need to generate, right? First thing that we do is to add an access to an interface we call a virtual. Then the interface name, which is the AXI_IF in ArcGIS, and then we'll be accessing it with an instance name VIF, right? So if you remember the interface AXI_IF, this is an interface name that we have, okay, in our code, and the same interface that we have utilized over here, right? So virtual is the keyword. So this way you get an access to an interface in an classes, right? So you need to add a virtual keyword, then the interface name and an instance name. So instance name is the name by which you will be accessing the different variables which are present in an interface in the class, right? We also required a data container, right? So when we call a get method of a mailbox, we need to specify a data container. So whatever data that we receive from the generator, we will be getting that in that data container, right? We also required one event, which is DRV next, okay? And this is the event that works between generator and driver. So as soon as we complete triggering an interface, we send this message to a generator by triggering DRV next, right? Then we added a mailbox, okay, which we named as an MBXGD, the constructor for the class where we take an argument as a mailbox, okay. This is exactly similar to what we've been doing in a generator also. So we start with the reset task, right? So we declared a task and we named it as a reset, right? Now remember, for our system, the type of reset that we utilize is an active low reset. So we need to apply a 0 to reset our system, right? So we start with an reset in. Now how you take an access of the ports which are present on your system is with the help of an virtual interface, right? So VIF, this is how we start, dot, then the signal that you want to access. So here we want to access and reset in, and we add a value of 0 to it, right? Likewise, for all the signals which are present in a design, we'll be adding a default value to them, right? So we have added a default value for an address write channel, then the write data channel, okay? Similarly, read address channel. So all of them, we have added a value of 0, right? So this is the default value for them, right? Then we wait for 5 clock ticks. So repeat 5 and then positive edge of VIF.clock. So we keep our reset for a 5 clock tick and then we remove a reset, right? So to remove a reset, the process is very simple. VIF.resetN equals to 1, right? So as soon as you apply an active high to a reset, this will remove a reset, right? And we also send the message to an user that DRV, this is the message that is generated by a driver reset done, right? This completes a task. So we have added an end task. So this is the first thing that we add in a driver, okay, which is used to reset the system, right? Now for each mode, the burst mode that we have for an AXI, we need to add a separate task. So that greatly simplifies an entire thing, right? In fact, we know that in a fixed mode itself, we have two different operations. We could either write the data in a fixed mode or we could read the data in a fixed mode, right? So for each of this operation, we will be having a separate task. So that greatly simplify the process of generation of a complex sequences, right? So let us first discuss fix write, right? So before we proceed to write this signal, okay, we actually need to draw some graph, right? So usually what we do is we create a simple sequences with our Verilog test bench, right? So like applying some of the signal and then analyzing the waveform. For example, here you could see, okay, so what we could just do is we could write the test bench code in a Verilog, okay, where we apply reset to be equals to 1, we make AW valid high, okay, and then we apply address as well as data, and then we just perform an execution of the code. So we get an first idea about a waveform, okay, how our system is behaving. So you could see when AW valid is high, right, this marks the start of a write operation. Then the next is when the slave is ready to accept the data, and that is conveyed with the help of wready, right? So this is the second step that we have. Then we complete the requested number of transaction depending on the length, the burst length that is specified, okay, and then we have a W last, right? So as soon as we have a W last in the next clock tick, you could see our B valid is high, and this marks the end of a transfer, right? So we start with an AW valid, then on each posage of a W ready, we need to apply a new data, right? So here we have a data, here we have a new data, here we have a new data, here we have a new data. Then we need to repeat this process, okay, for the length, right? For example, here AW length, which is specified as 7. So you could see we need to have the burst length of it. So we have W ready high for 1, 2, 3, 4, 5, 6, 7, and 8, right? So as soon as we have W ready high 8 time, we specify W last, right? So this mark an end of a transfer, and then we just need to wait for the response of a transfer, right? And then we could start the new transaction, right? So this is the typical behavior that you can easily get by writing a simple test bench. So you just need to apply, for example, apply some random value for WID, the length, the size, then make AW valid high, remove reset, okay, and then just analyze this behavior, right? So if you have this kind of behavior in your hand, right, so you could actually proceed writing the code for the task, right? So we name this as fixed, right? Okay, and this will take a transaction data. Now this is the data that we receive from a generator, which consists of values for some of a variable, right? The first thing that we do is we declared one variable which we named as length, okay? So AW length, since this is a write operation, so we are sampling tr, we are taking we are using tr.aw length plus 1, right? Now remember, whatever length that user specify, we add 1 to it, and then we are storing it in a length variable, right? We also send the message that this is the fixed mode, and that to a write operation, right? Then we wait for a positive edge of a clock, and we start applying a stimulus, right? So reset should be 1, AW valid should be 1 because we are performing a write operation, whereas AR valid, okay, should be 0 because we want to disable a read operation, right? And we know that AWID, which is a unique transaction ID that we need to provide for all the channels, okay? So we have declared one variable which is ID in a transaction class. So whatever value that is generated by pseudo random number generator for it, okay, we'll be simply applying it to an AWID, right? And this is the same ID that we are adding for a data channel also. You could clearly guess we are adding the same ID for data channel, and in fact for response also we'll be getting the same ID. So if you just analyze a waveform, okay, so the random value that we have for an AW ID is 9, okay, so when we receive a response, okay, you could clearly see the ID that we get is 9, right? Then we proceed, right? So we wait for a positive edge of a clock, then we apply the respective values to the different signal, right? So the ID is applied, then length, okay, so we are f.aw length, so this should be a length which is provided by a generator. AW size, now we already discussed we will be predominantly working on 4 bytes of data. For that, AW size must be equals to 0 and 0. So we are not capturing the random value that is generated by the pseudo random number generator. Instead, we are working on a fixed value. So as you have your first code working, later on you could just take the random value for an AW size, apply it over here, then verify the behavior for the random AW size, right? The burst type, now since this is a fixed mode, so burst AW burst must be equals to 0, 0, right? Then W valid must be equals to 1. Again, WID should be equals to TRID, and we assume that all of the len have a valid data. So W strobe equals to 4B all ones, right? As you have your first working code, again, you could generate the random value for a strobe, and then you could change which lane have a valid data. Here, we also make B ready one. So as soon as, so this basically suggests that master is ready to receive the response of a transfer, okay, as and when it is ready. And address, so whatever address, the random address that the generator generate for us, so we will be applying that to an AW address, right? Now here you could see the variable for which we required a random value is the AW length and an address, right, and an ID. So 3 variables required a random value. So you could just go to the transaction class, okay, and then there you could add the modifier, right? So AW length have a modifier. AW size modifier right now is not required, but as we have a working code, later on it is required. So for that reason I have added a rand modifier over here. Address requires a rand modifier. Okay, burst type also require rand modifier, right? So here you could clearly see, first we go to a driver code and then we decide which specific variables to have a rand modifier, right? So the code for fixed right is very simple. Okay, first thing that we do is whatever random value for a length that we get, we store it into the length variable. Then we wait for a positive edge of a clock and then apply the respective signal, right? So reset is high, AW valid is 1, AR valid is 0, ID for the address channel, then the length, whatever random length that we get, we apply to the system. Okay, the size is 010. This basically mean we are interested in verifying the behavior for 4 bytes, right? The burst type, since we are working in a fixed mode, okay, so burst value should be 00. W valid is 1. Again the ID, okay, which is same that we received from generator. Strobe, here we applied, or here we assume all the lane have a valid data, hence apply 1111, and be ready is also 1. So we are ready to receive the response from the sleeve for the transfer, and AW address is equals to TR AW address, right? For data, we are taking the help of the pseudo random number generator, okay, to generate the value for data. So u random underscore range. So this will basically generate the random value between 1 to 100, okay? Then okay, when we need to apply the next data, right? So this will be the first data that we're gonna send. Okay, so depending on the length that we have, so here length is, let us assume 7, right? So the burst length is 8, or we need to perform 8 transaction, right? So here we completed our first transaction. So when we need to apply the next data, because this is write operation, so we need to apply the next data, right? So if you just analyze the waveform, you could see our W ready is high, okay, and in the next clock tick we could apply the next data, right? And this is what we're gonna do. So we wait for a positive edge of a clock, we apply the address and data, then we wait for the W ready, right? So at the rate posage of VIF dot W ready. So we basically wait for W ready to occur, then we wait for one more clock tick, and then we start applying the next data, right? So here you could see we need to send the next 7 transaction, right? Here we are utilizing a for loop. So int I equals to 0, I less than length. So length is having a value of 8, so I less than 8. So this will be executing for 7 iteration, right? So we already completed 1 transaction, and this will give us 7 more transactions. So 1 plus 7 give us 8 transaction, and that is the burst length that we have, right? Here we wait for a VIF W ready and then positive edge of a clock, then we apply a data, okay, and here you could see we again follow the same pattern. That is, we wait for a positive edge on W ready, wait for W VIF dot clock, and then we again apply the new data, right? So this will be repeated 7 times. So as soon as we complete an 8 transaction as requested by a user, okay, we make W last 1, right? And as soon as W last is 1, we need to make, here we are making sure that we do not have a next transaction, okay? So we are making AW valid and AR valid both 0, right? So W last is 1, and then you could see we wait for a positive edge of a clock, okay, then we make last 0, right? So we need to make sure that W last is 1 only for a single clock tick. So we make it high, we wait for a positive edge of a clock, and then we make last 0, right? Then we need to wait for a B valid. So B valid basically is the signal that is generated by the sleeve, and we need to wait till we receive a high on B valid, okay, and then we capture the response. So here you could see we wait till the negative edge of our B valid, okay, before we proceed for the next transfer, right? So at the rate neg edge of VIF B valid, okay, and then we trigger DRV next. So as soon as we trigger an event, so now our generator will send the next event, right? So this is what we need to add in an fixed mode, right? Now remember, you need to follow the same pattern. So once you follow the same pattern, okay, handling or writing the monitor code becomes very easy, right? So if you use the different number of clock ticks and different signals, okay, for different sequences, then writing the monitor code also become complicated. So if you follow the same logic which you have utilized for one of a sequence, in that case the code for monitor could be greatly simplified, right? So we'll be utilizing the same logic, okay, for rest of the mode also, right?